So for each chapter, in addition to just posting the actual PowerPoint file itself, I'm going to be posting one of these videos where I'm going through the PowerPoint, kind of giving you a virtual lecture through the material. So the way that these PowerPoints are set up is that they're set up into focus groups. So for each main point out of the chapter, there will be a focus. So by the end of each focus group, you should be able to answer the focus questions, which will be the first slide for that particular part of the chapter. So for example, this first focus question is asking about the characteristics that an earth material needs in order to be considered a mineral. So I'm going to go ahead and tell you, I'm going to ask you this question on the exam. There are going to be 5 important components in order for something to be considered a mineral. So by the end of this section of the PowerPoint, you should be able to list those 5 necessary characteristics. So when we look at minerals, they are in everything around us, even things that we don't really consider when we're using them. Things like our toothpaste are made out of minerals. And then we have more obvious ones, like the rocks that we see outside, and maybe even the rocks that are on some of our hands as jewelry. So if you're going to study minerals, these building blocks of rocks, this is just the study of mineralogy. And humans have not only been studying, but using minerals for thousands of years. Even our first very early humans, as soon as we started developing tools and weapons, we started using minerals to do this. We would just chip them down into maybe like a spear and use them to hunt with, or create a sharp edge and use it as like a hammer. But we started to quickly progress from just using these very basic tools. And by the time we got around to the Egyptian civilization, we had figured out how to mine metals. Things like gold, silver, and copper. We could not only pull them out of the earth, but do some basic chemical reactions on them and be able to use the metals inside of these rocks. This was further enhanced whenever we got to the Bronze Age, when we got pretty good at chemistry and figuring out how to pull out small amounts of things like bronze out of rocks. But by the time we get to the Middle Ages, mining became super common. So mining is just going inside of the earth to retrieve either a mineral or rocks. It's not just the things that we find on the surface. We're actually going to have to go through a lot of effort and dig inside of the earth to mine. But this slide is one of the most important slides out of the entire chapter. With that focus question asking about the 5 characteristics that are needed to be a mineral, this is exactly what I'm talking about. So here, the geologist definition, there are 5 things that we need in order for something to be considered a mineral. They only have 4 out of the 5. They are not a mineral. So the first thing that we need in order to be a mineral is that things have to be naturally occurring. This means that they have to just be found naturally outside in our environment, whether it's on or inside of the earth. The second is that these minerals have to be inorganic. That means that they're not alive, they've never been alive in the past, and they'll never be alive in the future. So in geology, organic and inorganic has a very different definition than it does in, say, chemistry. So organic and inorganic in geology just means whether or not life is involved. So minerals are inorganic. They have never been alive. Minerals also have to be a solid. They'll never be a liquid or a gas. And this is because they not only have to be solid, but they have to have an orderly crystalline structure, which means that the way that the atoms inside of the mineral are arranged creates this repeating shape inside of the mineral. And then finally, minerals have to have a definite or a fixed chemical composition. So in this picture, we're looking at an image of calcite, a very common mineral that we'll talk about throughout the semester. It doesn't matter if our calcite is clear, like this one, or if it's a pink sample. All calcite is going to have the same elements inside of it. It's going to have the same exact chemical composition. And we're going to go over each of these 5 characteristics individually. So our first characteristic is that a mineral has to be naturally occurring. So again, this just means that it's formed out in nature. Even post-apocalypse, if humans are taken off the earth, minerals will still be around. But synthetic materials, things that are made in a lab by humans, they're not considered minerals. So for example, if you're looking to buy a nice pair of earrings, maybe diamond earrings are outside of your budget. So you look at cubic zirconia earrings instead. They look very similar. Cubic zirconia is just a lab-made diamond. But because it's man-made in a lab, it's synthetic, and therefore it's not a mineral, whereas diamonds form naturally, and they are minerals. The second important characteristic that defines a mineral is that minerals have to be inorganic. And again, there's a difference in our vocabulary here from chemistry. In geology, organic means alive. So inorganic just means something that's never been alive. So anything that is alive and is creating some kind of solid is generally not considered to be a mineral. Minerals have to be inorganic. They've never been alive. But this can get a little confusing because some animals make minerals. So for example, we're humans. We have bones, we have teeth. All of this are minerals. But our teeth themselves or our bones are not actually alive, even though they're a part of a living being. So we see that some animals do create these inorganic minerals. But they're only considered a mineral once they become part of a rock record. If I just pull out a tooth, it's not yet really considered a mineral. But if that tooth were preserved over a long period of time, it would be considered a mineral. So minerals have to be inorganic. But occasionally there's a weird one where some kind of living organism can create minerals, like a bone or a shell. But minerals always have to be solid. So if we have liquid or a gas, like water vapor, they will never be minerals. Minerals have to be a solid. So if we look at water, water has three different phases: a solid, liquid, and a gas. Liquid water and then that water vapor are not minerals. But ice is. The moment that it goes from that liquid water and freezes into solid ice, that H2O, that water, is a mineral. And there's a reason why the solid part is so important. And that's because minerals have to have an orderly crystalline structure. So all of the atoms inside of a mineral are going to repeat in the exact same pattern. Some of them might arrange themselves like little cubes or little pyramids. But whatever that shape is, it's just going to repeat itself over and over again inside of the mineral. So if we have all of our atoms arranging in a cube-like structure, like we can see here with sodium chloride or just our general table salt, when we look at the exterior, the whole mineral, instead of just looking at the atoms themselves, we're going to see that crystalline structure show up. So in our table salt, sodium and chloride bond together in a cube shape. We can't see the individual atoms with our naked eye. But when we have enough of them bonded together as a mineral, just looking at this mineral, we can very clearly see that cube shape to it. And then finally, minerals have a fixed chemical composition. So this just means that the elements inside of our minerals aren't really going to change from one sample to another. So think about table salt. If you've ever been to the grocery store to pick out salt, there are a ton of different varieties. You can get the Epsom salt with the little girl in her umbrella, it's like $1. Or you can pick out some pink Himalayan salt that might be $7 a bottle. It doesn't matter what color salt that is, or if it's a fine grain, small pieces of salt, or coarse salt, where there are larger chunks of salt. All salt has the same chemical composition. It's all made out of two elements, sodium and chlorine. So even though we can see salts that are vastly different colors. There are even black and purple salts. Although we can have a large variety of colors inside of our minerals, all types of salt are only going to be made out of sodium and chlorine. But we're going to see that there are some slight substitutions, and we'll talk more about this later. But for the most part, the chemical composition, the elements inside of a specific mineral, doesn't change between different samples of the minerals. So how is this different from a rock? If I taught this class like 10 years ago, Breaking Bad would be a great reference. If you've ever seen the show, there's a main character that gets really upset whenever his wife calls all of his minerals rocks. And a geologist is going to do the exact same thing. There is a major difference between a mineral and a rock. So minerals need those 5 characteristics. They have to be naturally occurring, inorganic, solid, with a crystalline structure and a definite chemical composition. But a rock is just a solid mass of minerals. So rocks are going to need generally 2 or more minerals in order to be considered a rock. So minerals make up rocks. Rocks are not minerals. There's a difference between the two. So if we look at granite, which is a really common and popular rock right now, you might have granite inside of your home as a countertop, or if you go to a nicer restaurant, they generally have granite tabletops. So there's a reason why granite is so popular right now, especially in the kitchen. And it's because granite is capable of withstanding really high temperatures, and it's a very strong rock. It's almost impossible to accidentally break it. And the reason why granite is so resistant to heat and so strong is because of the minerals inside of it. So we're going to see that rocks keep the individual properties of the minerals that they have. So when we look at this chunk of granite, we might notice that there are some darker colored minerals, and then a pink mineral, and even some almost white minerals. These minerals have different chemical and physical properties. But when we create an aggregate, or just put all of them together in one rock, this rock is going to have the properties of all of those minerals. So, for example, quartz, this kind of white-colored mineral in granite, is incredibly strong. That's why you don't even need a cutting board if you have granite countertops. If you want to chop a vegetable, you're never going to be able to break that granite or even leave some kind of knife mark on the granite because it's so strong, because it has a strong mineral inside of it. But we also have this mineral here called hornblende, this black mineral. And hornblende is very resistant to heating. So if you were to pull out something from your oven, you can put it directly on top of the granite without ever having to worry about it melting. Because hornblende can withstand thousands of degrees. So that 400-degree oven is not going to do anything. I have plastic countertops. If I tried to put something directly from my counter or from my oven onto my counter, it would melt within a couple of minutes. So granite is very resistant to heat and is very strong because the minerals inside of it have those properties. But again, we can have some outliers here. We do have some rocks that are not aggregates. They're only made up of one mineral. So, for example, here in Florida, our rocks are almost entirely limestone, which is made out of one mineral called calcite. So, calcite as a mineral and then limestone as a rock is something that we're going to discuss in almost every single chapter throughout our book because it's found throughout Florida. But it's also the reason why we have sinkholes here. And we'll get into more about this later in the chapter. But we also have some rocks that have some non-minerals inside of them. So they might be incorporating things like coal inside of the rock. So coal is organic. It's made from once living plant material. So even though it's not a mineral itself, it can still make up part of the rock. So that was the end of our first focus group, asking about the 5 major characteristics of the mineral. But now we're just going to start going through these focus groups. In this second one, It's going to be a review for a lot of you. We're just going to be going over the basic atom. So everything, whether it's a mineral or not, everything on our planet is made up of matter. And matter is made up of atoms, which are just the smallest possible particle that we can break something down into. So with atoms, we're going to have three really tiny particles inside of an atom. Atoms are things that are so small we need a microscope to see. But we can try to split atoms up into these even smaller particles, where we're going to have protons with a positive charge and neutrons with a neutral charge inside of our nucleus, inside the center of this atom. But we're also going to have these negatively charged electrons that orbit around the nucleus as well. So when we're looking at our atoms, we have these three different particles. But our protons and our neutrons, again, the two particles that are found in the center, in the nucleus, these are the only two parts that have a lot of mass. So mass is not only weight, but it's the space that something takes up. So protons and neutrons have weight to them, and they also take up space. If we look at this chart, we'll see that they are a lot larger in size than the electrons. But each of these particles are going to have different charges to them. Protons are positive, neutrons are neutral, they have no charge, and then electrons that are outside of the nucleus have a negative charge. So almost everything that we interact with has a neutral charge. But if you've ever touched like a door handle after wearing socks on carpet, you might have been shocked. That's because there's a buildup of electrons on that door handle or on your socks. So when we see things that are not neutral, we're going to see some kind of a reaction. But almost everything around us is completely neutral. That means that the charges of those positive protons and the negative electrons cancel each other out. So if it's been a while since you've taken a science class, you probably learned about the atom by seeing a diagram like this on the left. So that we saw our nucleus, kind of like the sun, and the center is the largest portion. And then surrounding it, we have these electrons that orbit around it, like our planets orbit the sun. But in the last few years, we've kind of moved away from this model. Because if we were to look at this, we might think that the electrons have a very well-known orbit around the nucleus. Just like we can figure out exactly what position our planet should be in around the sun. But this actually isn't true. We know that electrons are outside of the nucleus, but we don't know what kind of pattern their orbit makes. So what we do now is we draw our atoms as an electron cloud. So with an electron cloud, I want you to think of it like tree rings. If you ever looked at a tree that's been cut down, you'll see that there are these little concentric circles going out from the center of the tree. So at the very center of our atom, again, we have the nucleus, those protons and the neutrons. But surrounding it are electrons. And these electrons are going to make up clouds. And each cloud is basically just going to be like another ring or another layer of that tree. We're going to see that some atoms are going to be very small. They just have one or two clouds. Or we can have very large atoms that are going to have multiple rings of these electrons around their nucleus. So with this more up-to-date model of our atom, we're going to look at where these electrons are. Again, we don't know exactly where they are, but they're kind of like tree rings. We know that they're going to be somewhere exactly within this ring or the ring outside of them, for example. But these electrons are going to be able to move within each ring. It's going to be able to orbit around. So each of these rings is basically just called a principal shell. So within each shell, there's going to be a specific number of electrons that it can hold. We're going to see that these shells can hold a maximum of 8 electrons. So, for example, if we have an atom with the nucleus in the center, and then one ring with 8 electrons, because that's the maximum. If it has more than 8, then another ring is going to have to be deposited on top of it for those other electrons to go. So when we're looking at these different principal shells, or these rings of electrons around our nucleus, we're mostly concerned with the outermost shell here. These are called our valence electrons. That's because, with the exception of the first shell, every other shell can only hold 8. So if we have more than 8 valence electrons in the outermost shell, it's going to add on another ring. Once these principal shells have 8 valence electrons, they are no longer reactive to other things. They become stable. So we're going to see that only the electrons, these valence electrons in our outermost shell, are going to be the ones that interact with other atoms. Everything else is going to be very stable. So if we were to look at a periodic table, we would want to be able to quickly read some of these different elements. And one of the first things that we should be able to pick up from our periodic table is called the atomic number. And this is just the number of protons inside of the nucleus. And it's going to tell us exactly which element we have. So if we were to look at carbon, for example, it doesn't matter what carbon atom we're looking at. It's always going to have 6 protons inside of the nucleus. But if we were to add or remove a proton from that atom, it would no longer be carbon. If we added one, it could be nitrogen, for example. So changing the number of protons or changing the atomic number is going to change which element we're talking about. And on our periodic table, we're going to see naturally occurring and man-made elements. But in this course, we're going to primarily look at these naturally occurring elements, because these are going to be the things that make up our minerals. And we figured out a few centuries ago how to line these different elements up in a way that makes sense chemically. And we do this on the periodic table. So the periodic table, everything is lined up in columns. Don't read your periodic table as rows like we would reading a paragraph. We want to look at our periodic table column by column. So we're going to see that if we look at one individual column, everything inside of that column are going to share similar properties. And that's because the columns are determined by how many valence electrons are in that outermost shell. So if we look at the very right-hand column of our periodic table, these are called the noble gases. These are completely stable gases, things like neon that you might see in like a bar sign. Noble gases have full principal shells, which means that there are 8 electrons in that outermost shell. It's hit the maximum number it can hold, so it's going to stop reacting with things around it. So if you do go out and you try to get in a fight at a bar once they reopen, if you try to break open that neon sign and catch it on fire or throw acid on it, it's not going to react to anything because it has a full outer shell. It has those maximum 8 electrons in the outermost ring. But with the exception of these noble gases in the very last column, every other column is going to react to other atoms around it. But we're going to see that our minerals are made up of elements. And minerals are generally chemical compounds. This is just a fancy way of saying that there are at least 2 elements inside of it. So it might have both carbon and nitrogen. It just means that there are 2 or more elements inside of it that have been compounded or added together. So again, things that we use every day, like our table salt, it's a chemical compound. It's still natural, but it's made out of sodium and chlorine. It's 2 elements together, so it's a chemical compound. But we do have some minerals that are only made up of a single element, and these we call our native minerals. So for example, things like gold and silver and copper, it only has 1 element, so it's not a chemical compound. Instead, it's just a native mineral. So now we're going to move into how these elements can bond with each other. And we're going to see that there are 3 different ways that they can bond or join together, and how these different bonds create different strengths inside of our minerals. So we're going to see that all elements, with the exception of the noble gases, that very last column on the right-hand side of our periodic table, all elements form bonds, which just means that these elements are going to kind of link up and join with each other. And the reason why this happens is because when we have 2 elements that are bonding together, whether it be 2 atoms of the same element or 2 different elements bonding, it's going to lower the amount of energy that each atom has to put out. And overall, it makes them more stable. So think about the first time that you moved out. If you tried to live alone, it's very expensive. There's a lot of financial energy that it takes to pay your rent and your utilities, make sure you have food and gas. But if you wanted to lower the overall cost of your living, you might get a roommate or 2. Overall, it's going to lower the amount that you have to spend each month for your living expenses. And it's making you a little bit more financially stable. You might have more money to go out and have fun on the weekends. So just like getting a roommate instead of living alone makes you have to spend less money and be more financially stable, the same thing happens with elements. Just a single element out there on its own takes a lot of energy to exist. But if we can start bonding or joining these elements together, it's going to lessen how much energy they have to put out there. And it's also going to make them chemically stable. So we mentioned earlier when we were talking about those principal shells, they could hold a maximum of 8 valence electrons. So 8 is going to be the magic number when it comes to our chemical bonds. And this is called the octet rule. Octet just means 8. So if we have 8 electrons in our outermost shell of our electron, that means that it's full. It's not going to react to anything else around it. So the noble gases, that last column on the right-hand side of our periodic table, each one of those elements has 8 valence electrons. That outer shell is full, so it's not going to chemically react to anything around it. It's not going to be able to catch it on fire, explode them, or make them react to acid. But every other column inside that periodic table has less than 8 electrons in that outermost shell. So they're going to chemically react to other things. Overall, these elements want to have that maximum of 8. They don't want to have 7 or 6 inside of them. They always want to have 8 valence electrons because then they're stable. They don't have to react to everything around them. So, for example, if an atom had 7 electrons in its outermost shell, it might gain 1 to make it completely full. Or if we have an outer shell with only 1 electron, it would take a lot of energy to gain 7 electrons. So it's just a little bit easier for that element to lose or get rid of that single electron in that outermost shell. So we see that elements are constantly gaining, losing, or sharing their electrons, trying to reach that perfect number of 8 electrons in the outermost shell. But if we were looking at some of our larger elements, if we try to draw out rings for each shell of our electrons, it would get really messy. So what we use instead is called an electron dot diagram. So here, each red dot is just telling you how many electrons are in that outermost shell. Again, if it's not the outermost shell, we don't worry about everything that's closer to the nucleus. We only care about that outermost shell. So if we look at something like hydrogen, for example, hydrogen has 1 electron in that outermost shell. But if we were to look at something like neon, for example, that neon sign, it has 8 electrons in its outermost shell. So now it's stable. It's a noble gas that's not going to react to anything else around it. So in order to hit that octet rule, those 8 electrons in the outermost shell, we're going to see chemical bonds develop. So this bond just means that electrons are either gaining, losing, or sharing these electrons. Again, trying to hit that perfect 8 in the outermost shell. But we're going to see 3 different types of chemical bonds. And each of these, we're going to see that the electrons are going to be different, and whether they're being shared, they're just being moved around, or if they're going to be given to another element. But depending on what happens to the electrons, we're going to form different strengths in our bonds. We're going to have strong bonds that are going to be really difficult to break. We're also going to have very weak bonds, which are very easy to break. We're going to talk about each of these chemical bonds individually. So our first type of bond is called an ionic bond. Here we have our electrons actually being transferred. So if we were to have 2 atoms that are going to be ionically bonded together, this means that one of our atoms is just going to give up an electron to another atom. So we're going to actually transfer the electrons from one atom to another. So for example, if we are losing this negative electron, that means that this atom overall is becoming more positive. It's getting rid of that extra negativity and becoming more positive. But we're also seeing that one of our atoms is going to be gaining an electron. So if it's gaining an electron, it's becoming more negative. So it's a negative ion. We're going to see that these ionic bonds, when we have this transfer of electrons, it's going to make one atom positively charged, the other negatively charged. So they're going to be instantly attracted to one another. Think about throwing a magnet near your fridge. It's immediately just going to cling to the side. It's attracted to it. So these ionic bonds, the positive and the negative, are just going to be attracted together. And when they join, it's going to create these ionic compounds. And even though an ionic compound sounds something really complex, we're going to go back to our table salt, which is probably something that you cook with every day. Table salt is an ionic compound. It's made out of sodium, Na, and chlorine, Cl. And we're going to see that our sodium is going to lose an electron, and that chlorine is going to gain the electron that the sodium gave away. So as they become positive and negative, they're going to be attracted to one another. And because of this attraction between the positive and the negative ions, these ionic bonds create incredibly strong bonds. It's going to be very difficult to break them up. But we see that ionic compounds are going to be very different once we've bonded them together than if we were to look at the elements alone. So we talked about granite earlier and how it kept the individual properties of those strong and heat-resistant minerals. But ionic bonds do not follow with this. So sodium chloride, we all have it. That's table salt. But sodium and chloride, or chlorine, bonded together, it's totally safe. I don't have to worry about my table salt suddenly exploding inside of my kitchen. But if I were to look at just sodium itself, half of that salt molecule, sodium is something that is incredibly explosive. So if I had a piece of sodium about the size of my headphone case, and I dropped it in a bottle of water, it would create an explosion large enough to blow apart an entire airplane. So sodium by itself is crazy explosive. If we look at chlorine by itself, this is a lethal gas. Back in World War I, we used it as a chemical weapon because once you breathe it in, you're going to die from it. So sodium, I don't want to be around, and chlorine, I really don't want to be around. When they are on their own, it's just that single element, they're incredibly dangerous. But when they've been ionically bonded together as sodium chloride, it's a totally safe ionic compound. It's just our table salt. But our second type of bond is called a covalent bond. And this one is nowhere near as strong as the ionic bond. These covalent bonds are going to have like a medium strength in their bond. So here, instead of transferring our electrons from one atom to another, we're just going to have two atoms that are going to share the electrons somewhere between them. But if you've ever tried to share something with someone before, it's very easy for one person to just take it. And we can see this happening with our covalent bonds. And this is why it's just not as strong as actually giving that electron away like we saw with our ionic bonds. When the electron is shared between two atoms, it forms that covalent bond, which is a little bit weaker in its strength in comparison to the ionic bonds. And then our final type of bond is called a metallic bond. And these are going to be the weakest possible bonds. So here, these metallic bonds, it's not just two atoms that are sharing the elements. Here, the atoms are going to be shared between all of the atoms. This means that these electrons can move about the entire mineral. So if I had just an entire gold bar, it's made out of these metallic bonds. The electrons are not only going to be able to move from one atom to another, it's going to be able to move throughout the entire gold bar. And this is why these metallic minerals, things like gold, are great in electronics. Because when we can have atoms just moving through a metal, this is what creates electricity. So the next time you plug in your laptop or your phone, it's charging because the metals inside of it can allow the electrons to flow from one atom to another. And this is just called electrical conductivity. It's basically a little stream of electrons flowing through your electronic devices. But because these bonds are so weak, it also allows these materials to be malleable. And malleable just means the ability to be shaped. So think about Play-Doh. I don't have to heat up Play-Doh in order to bend it or mold it into a new shape. That's because Play-Doh is malleable. If we actually had just a chunk of pure gold, we could hold it between our hands for a few minutes and then suddenly be able to bend it back and forth because of this malleability. And then metals also have some other unique properties, like a luster, which we'll get into in a few minutes. So when we look at our minerals, there are certain physical and chemical properties we want to use in order to identify them or figure out exactly what mineral we're looking at. So because of the last 2 points of our definition of a mineral, they have that crystalline structure, that repeating arrangement of its atoms, giving it that shape, and the fixed chemical composition, where it's going to be made up of the same elements every single time. Each individual mineral is going to have very unique properties specific to that mineral. But we're going to see that some of the physical properties, the way that it actually looks, between different samples might vary due to small defects inside of it. But if we're looking at our properties, we're going to have two main types. We're mostly going to focus on diagnostic properties. And these are the properties that are going to be really useful in identifying a mineral. We also have ambiguous properties. And these are not going to be very helpful in helping us to figure out what kind of mineral we're looking at. And that's because these ambiguous properties are going to vary. If we look at, for example, 3 different types of calcite, they might look very different because of these ambiguous properties. But the diagnostic properties will remain the same in all of them. So one of our first diagnostic properties that are going to be really helpful is something called luster. And luster is just the amount of light that's being reflected. So think about jewelry. If you have a gold necklace or a gold ring, if you rotate that piece of jewelry under a light, you're going to see that the light is reflected off of the surface. And that's called a metallic luster. So we're going to see that some minerals, like here on the top, it's going to look like a chunk of metal. It's going to be reflecting a lot of light off the surface. So this is said to be a metallic luster. It just looks like a metal. But we're also going to see that a lot of minerals have a non-metallic luster. So if you're looking at your coffee table, for example, it's still a solid. Maybe it reflects a little bit of sunlight if it has a little bit of gloss on it, but for the most part, it's not reflecting anywhere near as much light as if you had a solid gold table. So these non-metallic lusters, there are a lot of different types, but these are the ones that just don't look like a metal. So if you're trying to figure out if your mineral is metallic or non-metallic in its luster, just ask yourself, well, I want a piece of jewelry made out of this. We wear jewelry because it reflects light. We like people to notice our jewelry. So ask yourself, does it reflect enough light to catch someone's attention? Does it look like it could be made into jewelry? And if so, it probably has a metallic luster. But the ambiguous property that we're going to talk about today, the one that's not important at all, is the color of our minerals. And that's because the color can be totally different due to impurities inside of the mineral. So if we backtrack a little bit, earlier we talked about how salt can come in different colors. It can be white, pink, or even black. Even though the elements inside of it are going to be sodium and chlorine, we might see an impurity in there. There might be a couple atoms inside of it that aren't sodium or chlorine. It's just going to have a slight impurity inside of it. And this impurity, even if it's just a single atom being included, that impurity is going to totally change the color of our minerals. So up here on the top, we're looking at fluorite. When you brush your teeth with toothpaste, this is the mineral that you're brushing your teeth with. But if we look at the color of fluorite, it can go from a brighter yellow to kind of a mint green to multiple shades of purple. And this is, even though it's the same mineral, it has the same chemical makeup, here we're going to have slight impurities. Again, maybe just a couple atoms that aren't supposed to be in there are going to dramatically change the color. So we don't want to focus on the color of our minerals. This is an ambiguous property. It's not going to help us figure out which mineral we actually have. But if we don't care about the color of our mineral, the one thing that we do care about that is diagnostic is called a streak. And streak is just the powdered form of the mineral. So if we could do this in class, I would hand you a mineral in what's called a streak plate, just this little piece of white porcelain. And if you were to rub the mineral against this porcelain plate, it's going to leave some powder behind. And sometimes the color of the streak, the powder, doesn't match the color of the overall mineral. So our streak is a diagnostic property. This mineral here is called pyrite. It's also known as fool's gold, because if you were to look at a piece in your hand, it looks like a giant chunk of gold. It's that brass, yellow, gold color. But if you rub it against a porcelain plate, the powder that's left behind is black. So we're going to see that this streak is way more important than just the overall color. I don't care that this is gold, but I do care that the streak of this mineral is black. But we're generally going to see that those metallic minerals, the ones that reflect a lot of light, are going to have darker colored streaks, and those non-metallic minerals are going to have a lighter colored streak, most of the time just white. But not all minerals are actually going to produce a streak. And we'll talk about this more when it comes to hardness. But if we were to rub a diamond, an incredibly hard mineral, against a streak plate, because that diamond is so hard, it's not going to leave a streak. We're not going to be able to powderize that mineral. But another important optical property is how transparent something is. So if we have something that is opaque, this means that no light is going to be able to pass through it. But we're going to see that some things are going to be translucent. This means that some light, but not an image, are going to be able to be moved through a material. So for example, you might have seen a bathroom with a frosted glass window. It's going to allow some light to come in from outside, but if you're showering, it's not going to have your neighbors seeing some indecent things. But most of our windows are completely transparent. That means that both light and an image are going to be able to move through this glass. And another really important part of our minerals are going to be the crystal shape. And this is the shape that a mineral would grow into if it had ample space to grow and could grow into the perfect form of itself. So this crystal shape is a little bit hard to kind of wrap your mind around. But if we look at this image, we can see that even though this is one mineral, we can see different shapes inside of this mineral. So for here, we have a hexagon. And over here, we have little cubes making up the mineral. So this crystal shape, it's just the shape that the mineral would grow into if it had enough space to grow. But generally, we see that the crystal shape doesn't appear inside of our minerals. And that's because most minerals form underground, in these kind of crowded environments, where they just don't have the space to grow into their perfect shape. They're only going to be able to grow into the shape that they possibly can fit into. But these crystal shapes can look totally different depending on what type of mineral we're looking at. We can have fibrous crystal shapes, kind of like the fibers inside of insulation. We can have bladed shapes, like the blades of a sword. We can have banded, kind of like tree rings. Or it's probably more obvious, these cubic shapes. But one of the most important properties of our minerals is just how strong these minerals actually are. And the strength of the mineral is totally determined by what type of bonds that mineral is made up from. If it has those ionic bonds, it's going to be a very strong mineral because of the strongest bonds. But if we have metallic bonds, the weakest type of bonds, we're going to have a very weak mineral. So this strength just determines whether these minerals are going to break, and if so, how much stress or pressure do they have to be under in order to break. And the strength is going to be directly related to the hardness of the mineral, or exactly how resistant is it to being scratched. So in geology, we use a hardness scale that's called the Mohs scale. And this scale ranges from 1 to 10. So on the scale, 1 is the softest mineral, 10 is the hardest mineral. But we're going to be able to very quickly figure out how hard a mineral is based by testing it with other materials. So generally, these are things that are going to be nearby. So for example, our fingernails are a 2.5 on this hardness scale. We can use our fingernails to scratch things. And if we can scratch a mineral with our fingernail, that's telling us that the mineral is weaker than our fingernail. So it will be less than a 2.5 on this scale. Another really common object is just a pure copper penny. This is harder than our fingernail. So we might be able to scratch a mineral with a copper penny, which is telling us that that mineral has a hardness of less than 3.5. And then finally, we might want to test our mineral against glass. But here we want to have the opposite way of thinking, because instead of trying to scratch the mineral, we're trying to use the mineral to scratch glass. So for example, a real diamond has a hardness of 10 on this scale. So that means that it's harder than a hardness of 5.5 of the glass. So if you take a diamond and try to leave your signature in a piece of glass, you're going to be able to do it just as easily as if you were holding a pen, because that mineral is harder. It's higher than a 5.5 on that scale. So that stronger mineral is going to be able to scratch that weaker glass. So this chart is just showing us the different hardness scales. Again, 1 to 10, going from the softest to the strongest minerals. And these are just some of the common everyday objects that we can use in order to narrow down our mineral strength. But what I want you to focus on most is your fingernail, this glass plate, and this streak plate. Again, if you can take something and scratch it with your fingernail, that's telling you that your fingernail is stronger than the mineral. So the mineral would have to be under 2.5. If we have a streak plate, this white porcelain plate, and we can leave a powder behind, that's telling us that the mineral is weaker than that plate. So it's going to be less than a 6.5 on the scale. So for example, let's say I find a mineral that I try to scratch it with my fingernail and I can't. But I can leave a streak behind. That's going to tell me that that mineral is somewhere between a 2.5 and a 6.5 on the scale. It's just going to help us narrow down the relative hardness of these minerals. And probably the hardest principle to grasp is something called cleavage. And cleavage is where we're going to have a mineral that breaks across the weak bonds. So we're going to need either those covalent or the metallic bonds in order to have cleavage. So the illustrations in Mastering Geology do a lot better job at describing this. But when we see cleavage in a mineral, because these atoms have that repeating crystalline structure, they're repeating the shape of the way the atoms bond together over and over. When we have cleavage and it's breaking across these weak planes, it's going to end up creating these really smooth, flat surfaces on our mineral. But not all minerals have cleavage. We're going to see that minerals either have cleavage, where they're going to break across these weak planes, or they're going to have something called fracture, where they're just going to randomly break as if I drop a glass on my floor. So minerals either have cleavage or they have fracture. They generally don't have both. But cleavage can also be confusing because it can be confused with the crystal shape. So we saw that some of those crystal shapes, like a cube, could develop if that crystal had enough space to grow into a cube. But if a mineral has cleavage where it can break into a cube, this can get a little confusing. So the easiest way to test whether you're looking at the crystal shape or the cleavage of a mineral is just to break it. If it breaks into the exact same shape, if I throw that chunk of cubic salt on the ground and it breaks into 5 pieces, the cleavage is going to cause each of those 5 pieces to also be a cube. If it only has the crystal shape and it has fracture, this just means that it's going to break into 5 just randomly shaped broken pieces because it doesn't have those weak bonds to break across. So our book goes into a lot of details about the different types of cleavage. I want you to focus on whether a mineral has cleavage or not. So these cleavages, we're going to talk about different planes. So a plane is just a flat section of that mineral. So for example, here we're looking at cleavage in 90 degrees. It just means it's making that right angle. And it's telling us it's 3 planes. So we're having 3 flat sides meet up each in 90-degree angles, kind of giving us this cube shape. So when you're looking for cleavage, look for flat, smooth sides, like we see here. They don't have to be perfectly flat, but relatively flat. And they're going to be meeting at these nice, crisp angles, generally either 90 degrees, or we're going to find them at 120 or 75 degrees. But if a mineral does not have cleavage, if it's only made up of those really strong ionic bonds, that mineral is going to have fracture because there are no weak bonds to break across. But with fracture, this just means that it's going to break into whatever possible shape it can. It's not going to break into these smooth, flat sides with nice, crisp angles between each side. Most of our fracture is going to be irregular. If I just drop a plate on the ground, I have no idea what kind of pieces or what shape those pieces it's going to break into. That's an irregular fracture. But we're going to see that some minerals have a special type of fracture called a conchoidal fracture. And we can see this here on the right, where it has this smooth, kind of dipped down surface inside of it. You'll probably meet my cats at some point. They like to sit behind me while I do these lectures. But they also love breaking my glasses. They like to knock them off on the ground. And if you've ever broken a glass, sometimes when you're picking up the big pieces, you'll notice this dipped, smooth fracture inside of it. And this is just called a conchoidal fracture. So again, minerals generally either have cleavage, they're going to break into those smooth, flat sides, or they're going to have fracture. They're just going to break into random pieces. But the rest of these properties, while they're still diagnostic, they're not quite as important as things like the hardness or the cleavage or fracture. But one thing that we should note is the specific gravity. And this is just a fancy way of saying how dense is our mineral. Most minerals have the same specific gravity. But if we look at metallic minerals, they're going to have a much higher specific gravity. That just means that they're a lot denser. They're going to be heavier for the same size piece. So for example, gold is 20 times as dense as water is. So if you have 1 cubic inch of like ice versus 1 cubic inch of gold, that gold is going to weigh 20 times as much, even though they're both going to be the exact same size, because that gold is metallic and it has a higher specific gravity. And there are some complicated ways to figure out exactly what your specific gravity is, but the easiest way is just to hold two of them, one in each hand. You want them to be relatively the same size. You just want to see if one feels heavier than the other inside of your hand. If they're the same size and one feels heavier, that means it's denser and therefore has a higher specific gravity. But some minerals are going to have special properties. And these special properties are going to be really diagnostic. They're going to be distinctive, meaning that very few minerals have them. So if you run across these special properties, it might be a giveaway that this is the mineral that you're looking at. So some minerals have specific taste. Halite, or table salt, tastes salty. Others have very specific feel. So graphite, for example, is very greasy. If you're left-handed and you've ever written with a pencil, you already know this. If you're writing left-handed, you're going to end up with grease stains along the side of your left hand. But talc, our softest mineral, it also has a very soapy feel. For me, it feels like those really thin bars of soap that you're going to get in a hotel room. It's kind of like this almost chalky, soapy feel to it. Other minerals might have specific smells. Sulfur, for example, reeks of rotten eggs. So if you've ever been around like a paper manufacturing company, it smells horrible nearby because they're processing sulfur. Some minerals are also magnetic. That means if you put a magnet anywhere near them, they're instantly going to be attracted. And then some minerals have very special optical properties. So calcite, for example, does something called double refraction, which we can see here. This is a transparent piece of calcite, which means that not only light, but the image can go through the sample. But what I want you to notice with double refraction is that it's kind of like putting on some drunk goggles. It's going to cause double vision. But here it's going to cause whatever is being read through that mineral to be refracted twice. There's going to be one copy on top and another along the bottom, one on top of another. And then finally, we're going to see something called effervescence. And this is, again, Mastering Geology has a very good video to show you what effervescence really is. And this is just if you were to put acid on top of some minerals, it's going to react. It's going to start bubbling up, almost in the exact same way as if you were to shake up a can of soda and then open it. It's going to start fizzing out and releasing carbon dioxide. Some minerals are going to release that carbon dioxide whenever acid is applied to it. So again, with these special properties, not all minerals have them. But if you run across one of these special properties, it's going to very quickly help you narrow down what mineral you're looking at. So now that we've gone over some of our common properties in our minerals, we now want to be able to break our minerals down into different groups. So On our planet, we have thousands of minerals. But even though we have thousands of them, only like 4 dozen of them are actually fairly common. So these really common or abundant minerals are what we call rock-forming minerals. These are the ones that we're going to see over and over again inside of our rocks. The others that aren't really very common are called economic minerals because we use these a lot in our manufacturing processes, and therefore they're worth a lot of money. So again, think about things like gold. There's not a lot of gold on our planet, but gold has a huge impact on our economy. So we have the common rock-forming minerals, and then we also have the less common economic minerals. So if we look at the chemistry of our minerals, we're going to see that the rock-forming minerals, those really common ones, are only made up of about 8 different elements. So if we were to look at the elements inside of these minerals, we're going to see that almost half of the minerals have oxygen inside of them. And then over a quarter of them have another element called silicon. If we look at these smaller parts of our pie chart, we're going to see some metals in there, things like iron and magnesium. We're also going to see salts, things like potassium, sodium, and calcium inside. And then if you look at this tiny little blue sliver, that's all of the other elements from our periodic table. So even though we have over 90 naturally occurring elements, we basically see 8 of them inside of these common minerals. So because silicon and oxygen make up 3/4 of all of these minerals, we're going to break our minerals into 2 different groups. The first are called the silicates. And these are where we're going to have both silicon and oxygen inside of that chemical formula. So a silicate is just a structure of how we're going to have one silicon atom that's going to be bonded to 4 oxygen atoms, creating this almost pyramid-like shape called a tetrahedra. So with these silicates, again, we need both silica and oxygen inside of that mineral. So if a mineral only has silica or oxygen, it is not a silicate, because silicates have to have both elements inside of them. And again, because silica and oxygen are so common, the minerals that have both of these elements are the most common minerals that we find on our planet. And these make up over 90% of our crust, where we live and where we access these different minerals and rocks through mining. Everything else that doesn't have silica and oxygen is going to be in our second group of minerals, which are called non-silicates. So these make up about 10% of the Earth's crust. So they're not very common, but most of these are going to be incredibly important for our economy. They might be difficult to find, but we're going to spend a lot of time and money accessing these through mining and then processing them to use to manufacture new materials. But we're going to start off talking about the silicate minerals, the ones that have both silica and oxygen. So we're going to see that the silica and the oxygen always bond together to form this tetrahedra. Again, this pyramid-like shape where we have one silica in the middle, and then it's bonded with these 4 oxygen atoms. Because the silica is so small, it's going to kind of get stuck between these 4 oxygen atoms, making an almost perfect pyramid shape. But these tetrahedra are going to start joining together. We're going to have them starting to line up and form chains. Just like if you have a chain necklace, it's made up of multiple pieces that are linked together. Or they might form sheets where we're going to form layers of chains, one on top of another. And we can also get some really complicated 3D networks of these crazy shapes of the way that these tetrahedra bond together. So I'm not going to go into the specifics, but the tetrahedra, again, they can start forming a line and all bonding together to form chains, or we can have a single chain if it's just one line, or if there are two lines, we can start forming double chains. But if we start stacking these chains one on top of another, we're going to start ending up with sheets, just like the pages in a book stacked one on top of another. But it's not always these nice chains and sheets that develop. Some of our minerals, especially those really hard minerals like quartz, are going to have these really complicated 3D networks. And these 3D networks are just going to be incredibly difficult to break up, which is why quartz is so difficult to break. It has a very strong resistance because of how complicated the tetrahedra are and it's in the way that they bond together. So we're not going to go into the details of these different minerals, but I want you to know some things about silicate minerals. So we're going to see that the most common silicate is called feldspar, and over half of our crust is made up of this one mineral. And we can see that up here, this kind of salmony pink mineral. If you look closely at granite, you're going to see a lot of this inside of it. Again, because it makes up half of our crust. But the second most common silicate mineral is quartz, also found in granite. Quartz is one that, because of impurities, can be a lot of different colors, from green to clear to black. But we generally see that these silicate minerals, when they break, when we cleave them and break up the tetrahedra, we are not going to be able to break into the tetrahedra. Instead, we're just going to be able to break between the tetrahedra. So we're going to see that our silicate minerals are going to form in three different ways. Most of it forms as we have magma cooling down from like thousands of degrees and then slowly turning into rock as it cools down. And depending on what kind of elements are inside of that magma and where exactly that magma is, it's going to produce different minerals. And we'll get into this a lot in Chapter 2. But most of our minerals form from magma cooling down and turning into solid rock. But we're also going to see that some of our silicates form through something called weathering. Weathering is breaking something down into tiny pieces. So if we look outside after a massive storm, we might see weathering. We might see little pebbles nearby, or even that the dirt in our yard has been moved around. So this is just weathering, which is how some minerals form. And then we see that some minerals form from extreme pressures. So think about diamonds. You probably already know that diamonds form really deep inside of the earth under extreme pressures. That extreme pressure is going to destroy most minerals, but it's necessary to form that super hard diamond. So although pressure or weathering can form some minerals, almost all of our silicate minerals form from magma cooling down and solidifying into a new rock. But when we look at our minerals, we want to be able to break them down into our light versus our dark minerals. So we're going to base this mostly on color, because the color is going to be dependent on what type of elements are inside of it. So if we look at our light-colored silicates, this can be anything from something that's totally transparent to white to light pink, light blue, light purple. It doesn't matter what color it is. It's just going to be a light shade of that color. And the reason why these minerals are light in color is because they're full of these salts inside of them. Things like potassium, sodium, and calcium. These salts are light in color. So it's going to make these minerals light in color as well. But salts are also very lightweight. So we're going to see that these light-colored silicates are not only light in their color, they're also going to be lightweight because they're full of all of these salts. So these slides are going to go over a lot of details about these individual minerals. I'm going to tell you what I think are the most important parts. So feldspars, these are the most common types of silicates. Again, it makes up over half of our crust. But the important things to know about feldspar is that we're going to find them in all three types of rocks: in igneous, sedimentary, and metamorphic rocks. Feldspars are also relatively hard. There are 6 on that hardness scale, which is another great reason why granite is great in our kitchen. But it doesn't matter if we get into the specifics of our feldspars. Again, I don't want you to worry about exactly the different types of feldspars, but I want you to know that feldspars are light silicates. You'll see here that all of these are light in color, but this also means that they're light in their weight as well, because they're full of these salts like potassium, calcium, and sodium. The second most common silicate is called quartz. Again, also found in our granite, and is also found in all three types of rocks. The important thing to know about quartz is that it's even harder than feldspar. Now we're at a 7 on that hardness scale, so this one is even harder to break than the feldspar is. But one of the most important things about quartz is that it generally has a lot of impurities. It's made up of silica and oxygen, but again, a couple atoms might accidentally get in there. And if these atoms aren't silica or oxygen, it's going to lead to an impurity, which is going to cause quartz to come in anything from like a darker gray to light pink, even to an almost orange color. But quartz is always going to have fracture. If you were to break it, it's going to break into a new size and new shape every single time, because it's made of those really strong ionic bonds. These last two silicate minerals, we're going to see things called muscovite. And here it says it has excellent cleavage in one direction. An easier way to think about this is the pages in a book. If we look at the book while it's closed, we can see that along the spine, we can see the pages of that book just stacked one on top of another. If I were to open that book, though, I'd be able to kind of peel or move one page from the next. Each page of paper inside of that book is going to have excellent cleavage in one direction. I can peel one page off from the page underneath it. Muscovite is going to do the same exact thing. Imagine that if I just stuck layers of packing tape one on top of another, I could go through and peel a layer off. And muscovite can do that. But you're always going to see this flat, smooth cleavage plane at the top. And then finally, clay minerals. These are going to be the ones that are made from weathering. Clays are just something that are so small, we can't identify them anymore. So if you go outside and dig in your yard, you're going to see that a lot of the dirt are actually going to be clay minerals. These are just going to be particles that are so small, we can't identify them. So we lazily just say, it's small, it's a piece of clay. But those were our light silicate minerals. We also have dark silicate minerals as well. And these are going to be darker in color and also heavier in weight. And that's because these darker silicate minerals are full of metals, things like iron and magnesium. If you ever held like an iron sword, they are incredibly heavy. So these metals, again, they're adding to the weight, but they're also giving these minerals darker colors. So with these dark silicates, we're talking about anything from dark gray to black, or even green. So we're going to see that even though this is a lighter shade of green, because it's green, it's telling us that there's a high amount of iron inside of them. Raw iron is green. So if we were to look at a green rock, it's always going to be considered one of these darker silicates. Because it has so much iron, it's giving them that green color overall. So looking specifically at these dark, heavier silicates, the most common one is called olivine. And this one is weird because it's one of the few where color is diagnostic. It's always going to have this olive green color to it, which tells you, again, that it's just chock full of iron. But we're going to see that olivine doesn't even form inside of our crust. It forms inside of the mantle of our planet. So it's going to be found deep beneath the surface, where it's incredibly hot. But we're also going to see pyroxene and amphiboles. These look nearly identical to one another. They're both black minerals, but the reason why they're darker in color, again, is because they have so much iron and magnesium inside of them. It's not only causing them to have a darker color, it's also causing them to have a heavier weight as well. And like we saw muscovite, that clear sample that you could peel apart, we see a darker silicate with the same kind of characteristic called biotite. Again, it's just like pieces of tape that you could peel one off of another. It still has excellent cleavage in one direction because the surface is completely smooth. But one mineral that I want to specifically mention is called garnet. Garnet's generally going to be kind of like a brownish red in color. But the most important thing about garnet is that it forms under these really extreme heats and pressures. So it's kind of like a diamond. You're not going to find it forming at the surface, but you're going to find it forming deep inside of the earth. So if I ever handed you a rock with a garnet inside of it, it could only be a metamorphic rock. Those rocks that are formed under intense heat and pressure deep inside of the earth. But we also have non-silicate minerals. Those minerals that are made up of anything other than silica and oxygen. So these non-silicates, they only make up less than 10% of our Earth's crust. So while they're not very common, economically they are super important. So with these non-silicates, we're going to not break these up into light or dark, but instead we're going to look at their chemical formulas. We're going to look at the last couple elements inside of those chemical formulas in order to group these non-silicates into other subgroups. So our first group is called carbonates. These are always going to end with CO3, 1 carbon, 3 oxygens at the end of our chemical formula. So for example, calcite. If you were to blow this up and look very closely, calcite has a chemical formula of CaCO3. 1 calcium, 1 carbon, 3 oxygens. Because it ends in that CO3, it tells you it's a carbonate. Carbonates are really important because these are the ones that are going to react to acid. So here, this mineral calcite makes up all the rocks in central to southern Florida. So calcite is a mineral that we're going to be talking about again and again throughout our semester. But we can also have evaporites. So think about having like a bucket of salt water that you're going to leave outside all summer. Eventually the water in that bucket is going to evaporate, but it's going to leave all the salts dissolved behind as an evaporite. So halite, or table salt, just forms whenever ocean water evaporates and leaves all the salts as a solid behind. So these are called our halides. But we can also have something called a sulfate. So a sulfate is always going to end in SO4, 1 sulfur, 4 oxygen atoms. But we're also going to see things called oxides that end in just oxygen. And oxides are really important because this is where we get most of our metal ores, most specifically our iron ores. We can take the small amounts of iron and chemically remove them from these ores to form things like iron for our buildings. But we're also going to see other groups called sulfides. Here, it's still going to have sulfur, but instead of ending in SO4, we're going to end them in SO3, just one less oxygen. And then finally, we have our native elements. Those minerals that are not chemical compounds. Instead, they just have one element inside of them. So things like gold or copper. So you'll actually need to go through and look at these different mineral groups of our non-silicates individually. But again, you're just looking at the last couple letters of this chemical formula to group these non-silicates. So with this has been Chapter 1. After you go through this material, please go through your Mastering Geology activity for this week, as well as completing your discussion post and your quiz. All of these assignments are due on Sunday nights before 11:59 p.m. If you have any questions about the lecture material or you need clarification, don't hesitate to reach out to me. Again, the best way to contact me is sending me a message through Canvas. Otherwise, I'll see you guys again for Chapter 2. Have a good week.